The next thing I want to talk about is something called colligative properties. Colligative properties are basically what happens when you dissolve something in a solvent. How does it affect the interaction among the solvent molecules? And of course, that's going to change things like how easy is it to boil it or melt it? How low of a temperature do you have to go to freeze it? What's the vapor pressure? All of those things are affected by dissolving something. So when I add sodium chloride to water, I'm changing the way the water molecules interact, and that's going to have an effect on things like the melting point and boiling point. I need to point out that this really only works for non-volatile solutes, that is, things that are dissolved. When it's a volatile solute, volatile meaning it has a fairly high vapor pressure, that changes the interaction, and some of what I'm going to talk about isn't directly applicable. Overall, this deals with what are called ideal solutes, things that behave the way we ideally envision them, kind of like the ideal gas law. So this is basically dependent upon, well, how many sodium chloride particles are there, sodium plus and chloride minus particles are there separating the water. So it's the ratio of the things dissolved to the molecules of the solvent. And what's an example of something that does that? Well, freezing point, like I said. If I have pure water, I lower the temperature, slow the molecules down, they form ice. If I have salt water, as I lower the temperature, I make sort of a slush. And eventually, as it freezes, the salt is left separate. So you can imagine how having Na plus and Cl minus interferes with the step here and prevents it from freezing. So, for example, salt lowers the freezing point. Now, did we actually do an experiment at the very beginning of the year where we used that? Yeah, I want to show you a couple of examples of ways in which people use this property. If you've ever been wherever, especially on the East Coast, if you've ever been there, you know that people dump salt on icy roads. What that does is it lowers the freezing point, and it ends up leaving the ice unable to refreeze. The salt breaks up the water molecules. We did that in our experiment in the beginning of the year, and it made it extremely cold, but not freezing, not able to freeze. Another good example, probably a more fun example, is this. You use it to make ice cream. So if you've ever used a classic old salt and ice freezer to make ice cream, you mix the salt in with the ice. That gets extremely cold because you're breaking the bonds, which is endothermic, takes energy from the ice cream solution, and it freezes. So this is my favorite example of colligative properties, and really the reason to learn colligative properties, if you're interested just in living a fun life, is understanding how ice cream is made, can be made. Other things that are related, boiling point is elevated by dissolved properties. That may be a little counterintuitive because even though I'm interrupting the interaction with the water molecules, you kind of think, well, that's probably going to make it easier for it to boil. If it's a non-volatile solute, that's not true. It actually, because for the same reasons we discussed, the enthalpy of solvation part, you have strong interactions among the water molecules and the salt. And so salt actually raises the boiling point, which means it's going to affect the vapor pressure. And I'm going to ask you, what should be the effect on the vapor pressure? If adding salt to water or dissolving anything in water raises the boiling point, what should be the effect on the vapor pressure? And of course, the effect is that the vapor pressure should get lower. Lower vapor pressure means it takes more energy to get the molecules going flying, takes more energy to boil it. This last one is called osmotic pressure, and it's really, really critical in biology. So this is a really classic experiment that one does in a biological lab. So this is a U tube. Yeah, that's what it's actually called. It's a U tube. There is a semi-permeable membrane here that allows water, but not water can pass through, but not the sugar. And this is sugar. This is glucose in this case. And so I'm going to dissolve sugar on this side. And a simple way to think about this is the water will tend to shift over in that direction to dilute out the sugar. So I have no sugar molecules on this side, and I have a fair number of sugar molecules on the other side. And the sugar molecules can't go back and forth, but the water molecules can. And because of the enthalpy of solution and it is a more complicated explanation, but you can think about it as a tendency of the water to want to dissolve the sugar more dilutely, to dilute out the sugar solution. I'm going to move water over here to that direction. And that's known as osmotic pressure. And that can be measured directly because the pressure of this height of water I can measure that directly. I know what the mass of the water is. I know what the square area is, the area on the tube. I know what the height is, so I know how much pressure is being exerted between these 2 points. The osmotic pressure, the water will diffuse over to dilute the sugar until it's exactly matched by the physical pressure of the column of water above it. This turns out to be really, really critical. Just think about it in terms of, keeping your blood cells the right shape and size, keeping plants. You may have discovered if you put a flower in water, if it's wilted, you put the flower back in water, it will soak up water and become more rigid again. That's all due to osmotic pressure. And you're going to be doing some work on it later in the year. Later next year, later in this calendar year, to look at osmotic pressure in biology. However, in order to look at these, we need to think about some other ways of representing concentration. So normally we represent concentration we use moles per liter or molarity. And that is really, really a useful unit of concentration. If what I'm interested in is when I add so many liters of solution, how many moles of the solute am I adding? So this is moles of solute over liters solution. But remember, colligative properties were defined as being affected by the ratio of the particles. And since when I dissolve something, the volume of the solution increases, I'm not really getting what I want out of a moles per liter. Another way I can do it is percent composition by mass. Mass solute. Now, if I know the molar mass of both of the things, that should be able to get me to how many particles of the solute are there in ratio with the particles of the solvent. That's an easy thing to do. That's a percent composition. The last one, and you're going to hate me for this, but I have to introduce it, is something called molality. And that's abbreviated a lowercase m, and that is the moles of solute over kilograms of solvent. And if I know the molar mass of the solvent, I can certainly get the moles to moles ratio. I know this sounds like it's pretty annoying, but it's really important that you be able to do it. And so you will get a couple of calculations on how to calculate the molality of a solution. So in that case, you're not measuring the overall volume of the solution. You know how many kilograms of water you had, that's the solvent. You know how many moles of solute you added, and you really don't care what the final volume of the solution is, because the ratio of the moles to the moles, moles of solute to moles of solution, of solvent, is really what you're interested in. And so those tell you how to calculate. That's one of the more easy concentration units to use to determine what the colligative properties will be. How will the properties be affected by the dissolved solute, sorry. So what is the molality of 5 grams of NaOH dissolved in 1 liter total of water? So a couple of things here. I'm not talking about a liter of the total solution. So I'm going to need to know how many grams or kilograms of water. You may know that, let's assume the density of water is equal to 1.0 grams per centimeter cubed, which is the same as 1 kilogram per liter, right? Because there's 1,000 milliliters in a liter, 1,000 cubic centimeters in a liter. All right, so I know that I have 1 kilogram of water. What's the molality? Well, you'll have to figure out the number of moles of NaOH. So it's 5 grams of NaOH times 1 mole over 40 grams. That's the molar mass. And so 5 divided by 40, 0.125. That's the molality of that solution. There's another new concept I have to introduce, actually not that new, and that's known as the Van 't Hoff constant. And that's an easy one. How many particles do you get from a mole of sodium chloride when you dissolve it? The abbreviation for this is I. So it's basically asking, when I dissolve something, how many particles come out? So for example, if I have C6H12O6 glucose, 1 mole, and I dissolve that aqueous, I get 1 mole of the dissolved C6H12. And so the Van 't Hoff constant is equal to 1. It's a 1-to-1 ratio. If I have 1 mole of sodium chloride, I dissolve that in water, I get 1 mole of Na plus a mole of Cl minus. And so Van 't Hoff constant in this case is 2. And my question for you is, what's the Van 't Hoff, what's I for CaCl2? And it shouldn't take you too long to figure out that I is equal to 3 in that case. And so when I'm talking about how many particles, I have to keep track not just of sodium chloride. I don't have sodium chloride molecules floating around in water. I've got a 1-to-1 ratio of Na plus Cl minus, right? So I have to account for all of those. So in figuring out colligative properties, if I'm trying to figure out the vapor pressure, for example, or the osmotic pressure, is often given as I times the concentration times the gas constant times the temperature in Kelvin. So that's concentration R is equal to the gas constant. Inexplicably, in biology, they're going to use a unit of pressure called bar. I don't know why. 100 bar is 1 atmosphere, and then T is Kelvin. So you'll be able to calculate the osmotic pressure if you know the concentration, the gas constant in the right units. I'm going to be talking in kilopascals, not bar, and the temperature in Kelvin.